Towards the cloud this time. All right, so yeah, we're going to find the arc length of x equals t squared plus 1 and y equals 4t cubed minus 1. All right, so nothing too crazy in terms of the derivative. But you can see that we're popping it into the formula for the arc length. So that's going to make things a little juicier, but it shouldn't be too crazy. So I'm going to find. I'll rewrite it just like I've been doing. I'll rewrite the x function, so t squared plus 1, and the y function, 4t cubed minus 1. So we have dx dt is equal to 2t, dy dt is equal to 12t squared. All right. So those are the values that are going to go into into my integral formula. So I'm looking at s equals on the interval of 0 to 1 because it gives us the t values. Now we'll have to really kind of get into domains a little bit in more detail down the line, but for now we're just assuming that that's an appropriate set of boundaries that we're not, and it's a reasonable assumption to make because we're looking at two functions that are continuous differentiable functions in one variable, right? So with that in mind, we have no expectation that there would be some sort of discontinuity or a point of non-differentiability along the interval of 0 to 1. So not really worried about any kind of values of t that would break the functions. All right, so integral on the interval of 0 to 1, we got the radical, the dx dt is going to be 2t. We're going to take that value and square it, plus dy dt. We're going to take that value and square it. That value is 12t squared. And then we get a dt. So a little bit of cleaning up has to happen in order to be able to work this out. All right, I'm not always going to ask you to do stuff by hand, but I will sometimes ask you to do stuff by hand, and you won't know under what circumstances I'm going to ask you to find an integral or a derivative by hand. So you got to be prepared in all situations. So I'm just going to go through this one by hand and just play it all out. So we're looking at 4t squared plus 144 t to the 4th dt. All right. Now I see that there's some common factors here. We have a common 4 that can be pulled out. So I'll show the intermediate step. I'm going to go to black for those keeping score at home. I'm going to pull out a 4, and I could also pull out a t squared. All right, so when I pull out a 4, gives me a 1. Divide 144 by 4, it's the same as dividing by 2 twice. So it's going to give me a 36 t squared dt. All right. That factor of 4t squared is perfect. So I can pull it out, not only of the radical, I can pull it out of the whole thing, but I'm just going to pull it out of the radical. I don't want to go too crazy here. So 2t square root of 1 plus 36t squared. Overboard with my radical, and then we have the dt. All right, so then it's really just a question of, all right, well, I got to integrate this, so by what method? And so it looks like it's a U substitution situation. And I can say that fairly confidently. I mean, if I'm a student, fairly confidently. As a teacher, I better be more than fairly confidently. I'm just going to resize this a little bit. Because if I were to take the derivative of the innermost function, the 1 plus 36t squared, I'm going to get an expression, a monomial that's raised to the first power. So that's going to help me cancel out the 2t on the outside. So I'm feeling pretty good about that substitution. And specifically, that substitution would be, let me just bring it in over here, u equals 1 plus 36t squared. All right. So, you know, with integration skills, I have my own way of saying things, but one of the things I like to say in Calc 2 is when you're diagnosing what sort of technique to use in order to integrate, you don't work with the most complicated concept first. You start from the beginning of the course and work your way to the end. All right, so is it the reverse of the power rule? No. All right, what's the second thing you learned? Use substitution. Let me try that. Because as you remember vividly, I'm sure, the course got, in terms of the techniques, got more and more challenging as you went along. Yeah, there was some little nuggets in the later or latter part of the course where it's like, oh, surprisingly, this was not difficult. But there were mostly topics that just cascaded and became more and more challenging. So start with the more basic concepts and then go from there and see where you end up. Right? And, you know, generally, if you're looking at a product of two functions, you know, you might start thinking of something like integration by parts, but I'm seeing a power relationship here with that radical. It's raised to the 1/2 power. So I'm thinking that somewhere along the lines of reverse of the power rule should come into play, if only we didn't have such a beefy 1 plus 36t squared. If it were something much simpler like a u, things would be a lot nicer. So that's what we're going to operate with. So we have du equals 72t dt. All right. Now, I want to make this u substitution help me cancel out, because I already know I can get rid of the 1 plus 36t squared. I want it to help me cancel out the 2t dt. There's a couple of ways you can handle it, but I think the most convenient way would be to say, all right, well, I have a 72t dt. I want that to become a 2t dt. So let's divide it by 36. Oops. I'm going to take my shape draw tool off. So divide by 36, divide by 36. And we'll get 1 over 36 du is equal to 2t dt. And that's where we're going to get our clean substitution, which is ideal. I mean, it's expected, but it's also a very nice outcome. Right? That's what we're looking for. All right, we could start going after it like an animal and make our substitutions, but if we do that, then we've neglected the boundaries of integration, and we don't want to do that. We want to make sure that we've accounted for all aspects of this function. If I'm converting from the variable t to the variable u, and I know that 0 and 1 are t equals 0 and t equals 1, I got to make that substitution. Right? So what I'm going to do, just off on the side here, is I'm going to find u of 1 and u of 0. All right, if I plug in a 1 to my u function for t, I'm going to get a 37. All right, not ideal. I mean, you took something that was fairly nice and clean, a nice 1, and you made it into something that's less clean. Still, at least it's a whole number, which is something. Plug in a 0 and you get a 1. All right, so that didn't end up being too crazy, but these are the new bounds of integration. All right, so you're getting like a little capsule summary of some of the earlier parts of Calc 2 here. So S would be equal to the new integral is going to be on the interval of 1 to 37. All right, instead of my 2t dt, I'm now going to have a 1 over 36 du. All right, so I can just kind of tuck that in here. If I want, I can just put the 1 over 36 on the outside. I shorted myself some room. I can move things easily, but I don't want to. Partly because I don't know who's writing in pen, and I don't want to make you have to scratch all this stuff out and change it. So I'll deal with it. We have the 1 over 36. I'll put the du. I know the du is going to have to be at the end, so I'll just throw that over there. That I might end up moving in a sec. But then I have my radical. And that radical, instead of containing the 1 plus 36t squared, we know 1 plus 36t squared is equivalent. And I'll just do a little highlighting here. For clarification purposes. That's equivalent to simply just a u. All right. So I am going to move some things a little bit closer just for the sake of convenience. And actually it looks all right. I did move the u a little bit over, but I think it's okay. All right. So S is going to be equal to, and I'm still going to leave the 1 over 36 inside. You have my 1 over 37, 1 over 36. I'm going to write it as u to the 1/2 du. Reverse of the power rule. So we get out all that for a drop of blood. We finally get to a point after all of that work where we can take the antiderivative. So increase the exponent by 1 and divide by the new exponent. When you divide by 3/2, it's the same as multiplying by 2/3. So we're taking 2/3. I'll just show the step. 2/3 multiplying it by 1 over 36. So you're talking about 1 over 54 because the 2 is going to go into 36 18 times. 18 times 3. So 18, 36, add another 18 onto that. 46 plus 8, 54. All right. So we get S equals, I actually took, sorry. I actually took the antiderivative, but then I just still put the stuff. I put the stuff in the things. Why would I do that? Who knows? Why does anybody do anything? All right. Yeah, it's the act of integration. We're done with that stuff. The 1 and 37 we go right, yeah, and right, yeah. That was a Monday mistake. It's not even Monday. I had like a Monday morning mistake. So I know it's the 1 over 54. I got the u to the 3/2. And again, that's happening over the interval of 1 to 37, or such that u spans the interval of 1 to 37. So now I just got to substitute. There's no expectation that you're going to somehow figure out what the square root of 37 is in your head. I mean, it's going to be a decimal value, so we're going to have radicals in our answer, and there's nothing wrong with that. Right? So S would be equal to 1 over 54 times 37 to the 3/2 minus 1 over 54 times 1 to any power. It's just going to be 1, so it's just minus 1 over 54. All right. We were not given any units, so we don't need to include units. I mean, you could write the word units, but I'm not going to lose sleep over something like that. You could factor out a 1 over 54. That's another way of going about it in terms of cleaning it up. You could make the 37 a radical and then cube it. I mean, it's all kind of serving the same purpose of just changing the form of it without actually adding any kind of true meaning to it. The only time you'd ever get a sense of what this is really giving us is if you convert it over to decimal form. But I would even caution you in saying that you do that and you get a number, and I'm sure you've done this before in some problems. You convert it over to decimal form, and then right afterwards you say, why did I do that? What did I learn from that? All right, so it's 1.789. Okay, there's no context here, so I don't know what I'm looking at, you know. So if you tell me that a road can be mapped or modeled by the parametric equation given, and over the course of 1 hour, where t is measured in hours, so 0 to 1, how much distance was traveled along that road, kilometers, miles, whatever. Now you have a meaning behind the decimal equivalent, and you also have a meaning behind units, right? But when you have a stripped down problem with no context, just the fractional form is fine. So, you know, and this isn't your first rodeo, so you've seen ugly answers before, but you know, this kind of problem in my mind is really here to sort of drive the point home that, you know, like don't do the extra work unless you need to, right? Because I'm confident that you could all type these numbers into a calculator and get an answer. That's not what I'm measuring here, you know, in terms of ability. All right.
I have a quick question.
Sure.
Is there a way to do this without changing the bounds from 0 to 1 to 1 to 37?
Yeah, you just integrate with a boundless function, so leave the boundaries out completely. Integrate, reverse substitute so that it's all back in terms of t, and then work with the 0 and 1.
Okay, because I learned both ways, but it's been a while. But I think that's what I normally did, because I vaguely remember learning to change the bounds, but I think that.
Right, and that's fine for now. Later in the course, just to give you a little heads up, we're going to be doing a lot of work with converting from one variable to another, you know, one type of variable to another. So at some point, you're going to have to make the transition, but for now, it's fine to go either way.
Okay, thank you.
No problem. All right, so the next one, arc length again, right? But this time it's a trig problem. So, and you know, that's part of it, you know. So the concept itself, I mean, if you're relying on, and I remember it's dangerous territory when you're taking math classes and science classes, it's like, oh, as long as I have all the formulas, I'm good. And then you come across a problem like this and you're like, yeah, okay, so I'm good for the first step. Then what? You know, so there's all sorts of ways to look at it, but the skills are probably even more important in this course than any other course, because especially, I mean, we're in a remote environment, so we're looking at everything as an open notes kind of thing. But that doesn't mean it's going to be easy, you know. So yeah, the skills are what we want to hone. Right. So again, I'm going to rewrite the function. It's that extra step, but for me, it makes all the difference, because and you've seen this before, I think, so far. I've made a couple of careless errors here and there, not even just today, just like repeatedly ongoing, where it's just like I misread the problem. I didn't carry down a number the right way. So, you know, it forces me to kind of like lock in on the problem. So it's a me thing. If you want to just jump right to it, that's fine too. All right. In both cases, we have a product of two functions, t and sine of t versus t and cosine of t. So in both cases, since we need dx dt and dy dt, we need to use the product rule. So the first function t times the derivative of the second, derivative sine is cosine, plus the second function sine of t times the derivative of t, which is just 1. So I could just leave it as sine of t. dy dt. First times the derivative of the second, the derivative of cosine function is negative sine. So negative t sine t plus my second function cosine t times the derivative of that first function again. And there we are. Yeah, because derivative of t again is 1. It's not going to change anything. So you can already see that we're tackling a different. I just painted myself into a verbal corner there. Tackling a different what? Like player, running back? I don't know. So that happens sometimes. Like the Ace Ventura moment. Ace Ventura 2, When Nature Calls. If anybody knows what I'm referencing, I'll be shocked. I'll show the video at some point. Right, so S equals, still in the interval of 0 to 1.
Did you do the derivative of the first plus the second? I guess it doesn't matter if it's commutative.
Correct.
Right? Okay, cool.
T cosine t plus sine t plus negative t sine t plus cosine t. And usually I make my radical bars too long. This time I made it too short. So that's all right. Now I made it too long. There we go. That's the TED we all know and love. So dt. All right, so the sum of the squares radicalized, and now we just got to carry out the process. It's a particular brand of fun. So S equals a little distributive property. It's a binomial squared, so we're going to go that route. Hopefully, some things will clean up. I'll write the radical in later, / if I forget, please remind me. So t squared cosine squared t. The outers would each be t sine t cosine t, so we're going to have 2 of those. Plus sine squared t. And when we get on to the second binomial squared, we're taking that negative t sine t squaring that. We're going to get positive t squared sine squared t. Then the outer terms, we're going to get a negative t sine t cosine t, and again 2 of those, which is great news because that's going to cancel out the beefy part of the other trinomial. So, and I'm going to have to move some things over and clean it all up in a second. 2t sine t cosine t. So, again, this ability to move and resize, it's a good resource. So, I'm not saying you have to pay for an app, but if you see stuff like this and it's like, oof, I'm really considering getting an app. Which one do you recommend? That's part of the fun, I guess. So cosine squared t, and then a dt at the end, and let me just get that radical in before somebody calls me out. That's right, I have fun. All right, quick double check Garuski here. We had the t squared cosine squared t. We had the inner terms and the outer terms put together, sine squared. I didn't miss that. The first term was good. For the second binomial squared, you have the canceling term, which we'll take care of in a second, and cosine squared. So far, I don't think I screwed it up, which is like a new world record. Cancel. All right. Now we have a lot of great stuff happening here, but there's one part of it that's extra beautiful. I'm going to rewrite it just because people, especially if you're a little weak in the trig area, which 3 classes in a row, right? So you now will know that this is a big deal. 3 classes in a row. I will in a second have talked about how important it is to know unit circle and your trig facts, right? So it's important. I keep bringing it up, right? So the Pythagorean identity. So if I reorganize, I'm going to get sine squared t plus cosine squared t, and then plus a t squared. I like to keep the signs first. Sine squared t plus t squared cosine squared t. Still under the radical. With the dt. All right. Now I'm going to highlight the part, the beautiful part. And then I'll highlight the best friend of the beautiful part. All right. So I'm looking at s equals 0 to 1. Sine squared plus cosine squared is your Pythagorean identity. Sine squared plus cosine squared is equal to 1. I'm also going to highlight that so we know that that corresponds with the other thing that I highlighted in the same color. All right. For the second piece, I'll show the intermediate step, but we have a common factor of t squared. So I'm going to pull that out. And when I pull out the t squared, you'll see that I also have a sine squared t plus cosine squared t. And here, instead of showing it in an additional step, I'm just going to X it out because that 1 that is going to cancel to is going to multiply by the t squared and actually be truly the definition of a cancellation, right? So this is going to wipe out. Pre-calc strikes again. We have the integral on the interval of 0 to 1 of 1 plus t squared. Oh, why did I go with the ugly good looking? Yeah, that's the good stuff. 1 plus t squared dt. All right. So good looking radical, good looking integral. The problem is it's not really any easier than the problem before it because there is no outer function, right? So we can try to do a reverse power rule. We could try to do use substitution, but that's not going to work. We can try to do integration by parts. We can try to do not improper fractions. Well, you could try improper fractions, but you could try to do partial fractions, but that wouldn't make sense because it's not factorable. So you go down the list and you work back and forth through the course and you start deciding, well, really maybe not deciding. You kind of start doing the opposite of deciding. You start narrowing it down by saying, well, it's not that, it's not that, it's not that, hoping that it's not the one thing that you settle upon. All right, and that one thing. Sorry?
Can you just put 1 plus t squared over 1/2? I mean, to the 1/2?
The 1/2?
Yeah.
You could, but then you'd be stuck. There's no way to integrate that using the reverse power rule because you would have an inner function that has a derivative of 2t, and that would be introduced into the process. Okay? So it all falls apart there. Really, the only way to integrate this is, you guessed it, trig substitution. All right, so we thought we were done with the trig, that all the trig canceled away. This is going to be so easy. But no, we got to bring back some trig in order to make it all work. Now, we might not like that, but if you really consider what's happening here on this page, just this one page, we're reviewing all the techniques of integration, all the really important ones from Calc 2. so while it might be a pain, it's a good pain because it's better than me saying, hey, put it in your calculator, get an answer, and then throw it on the test and say, yeah, do this one by hand. You'd be like, oh crap, I didn't know I was supposed to know that. You know, so yeah, it's all part of the plan, as they say, whoever they are. So we have S equals the integral on the interval of 0 to 1. So that part I'm not worried about because that's going to work itself out. It's that beefy radical. All right. And so I need to create a substitution, a trigonometric substitution. And part of the challenge of that is knowing that it's trigonometric in the form of the substitution. But like I said before, that's the process of elimination component of everything. You say, well, it ain't this, it ain't this, it ain't this, it ain't this. What's left? Well, okay, it must be that. All right. So hopefully you didn't throw away your Calc 2 notes, but if you did, just go to my Calc 2 page on my website. It's all there, videos and everything. So anyway, what we want to do is label up a triangle that's going to have at its core this relationship. And I always teach trig substitution, and without hopefully not teaching it again right now, but I'll give you the short version, but also my spin on it. I teach it by not really talking about the rules. I teach it by just saying, here's a triangle. You have two values that you can work with, right? Because the model is in the form of the square root of a squared plus u squared. All right. So let me just tuck that in over it. Want it to look halfway decent though. All right, so that's the form that we're looking at. All right, so if that's the case and I want a and u, then I'm really just taking the square root of the constant term and I'm taking the square root of the variable term. All right, so I would come up with, and I'll just make a note of it on the side here, a equals 1, because a squared is equal to 1. All right. It's a geometric situation. So with scalar values, not vector quantities. So we do not care about negative lengths, right? Only positive lengths, right? The u would be equal to t. All right. So what's going to happen is one side of this triangle is going to be equal to, and so I'll put the quotes, I'll put quotes on the a and the u because we're not really going to use those values too much. It's really just to kind of get us to these values here, right? It's just giving us a sense of the model, the 1 and the t. So I needed to look at that radical and say, what are the important values that I can pull out of this? And the answer is the 1 and the t. So what I want to do is I want to place the 1 and the t on the triangle in such a way that the third value, or the third side would be equal to the square root of 1 plus t squared, all right? So you have 3 sides to choose from. You put them anywhere you want, as long as whatever the third side is computes out to be equal to 1 plus t squared. All right, so what I'm going to do is I'm going to put the t here. That is not a pen. Undo. Yeah, there we go. And I'm going to put the 1 here. All right. I could have done it the other way around, and it would have been perfectly okay. I just chose to put it here. As it turns out, the trig function would be just reciprocal, as opposed to, because we're going to come up with a tangent function in a second. If you did it the other way around, it would have been the cotangent, but it would have worked out in the end anyway. With the same number of steps, same level of difficulty. So you really can't go wrong, because when I use the Pythagorean theorem, the missing side here is the square root of 1 plus t squared. All right. So I have a well-labeled triangle. Now I need to get some substitutions out of this. So what I do is I develop a ratio and a secondary ratio. So primary and secondary ratio, 2 ratios, one of which is going to relate the variable u to a.
You're not sharing your screen, Professor, so we can't see what you're doing.
You can't, nobody can see what I'm doing?
No, you're not sharing your screen. It's
I can.
no.
I can see it.
I'm sharing it on.
I can see it too.
Really?
It might be,
Alright, Zoom.
it might be an issue on your end.
Yeah, I have spotty internet and it keeps leaving. I don't know why I can't see it.
Yeah, that might be the issue. Yeah,
I would leave the meeting and come back, so maybe you.
that might be the way to go.
I don't. I'm gonna exit out the class and then come back.
Yeah. All right. So the one ratio is always going to be the u over a. Right. So in this case, that corresponds to the ratio of t over 1. Now, what ratio is that? Well, if I'm looking at the reference angle of theta, I'm looking at the opposite side and the adjacent side. All right, so that makes that the tangent ratio. So tangent of theta is equal to t. All right. So that u is always the variable part, right? So the single variable. The a is the constant. All right. I make a note of that because people always forget the u and the a, but they remember, okay, the variable goes on the top, whatever that loose variable is, that's going to be on the top of my fraction, whatever the constant is, that's going to be on the bottom. All right. Then we're going to have another ratio that is the square root based off of the model that I gave, a squared plus u squared over the a value. So that's the radical part divided by the constant. Right? So if we're looking at it from that perspective, so again, specifically from the perspective of theta, we have the hypotenuse, but we also have the adjacent. Right? So hypotenuse over adjacent, oops, sorry, jumped on me. But hypotenuse over the adjacent will be the secant ratio. All right. So making a little note, the radical part was the 1 plus t squared. The adjacent part is a 1. And that's equal to the secant ratio, secant of theta. All right. So we have all that stuff, all that fun stuff. Now it's a matter of making the substitutions. You pick up a pen and drop it, and get another water bottle.
Can you scroll down a little bit? Sorry. No,
You have
down.
it?
Yeah. Oh, okay. Just the bottom of the page. Thank you.
No problem. All right, and so I'm looking at a relationship on the bottom of the page there where I have secant of theta is equal to 1, the square root of 1 plus tangent squared. That is equivalent to secant theta. So that's great. I have to get rid of the dt though. All right. So what I'm going to do is I'm going to choose the easier of the two models. One of them, obviously, I'm just by the look of it, has less going on. The tangent of theta is equal to t. And I'm going to solve that for t, which isn't going to take much doing. But then in that process, I'm going to take its derivative to create a dt out of that whole thing. Right. So I'll carry on the process up here. So we'll have t equals tangent of theta. And then dt, well, dt d theta, I'll show the intermediate stuff. dt d theta is equal to secant squared theta d theta. Oh, it won't be d theta yet. In the next step, it'll be dt equivalent to secant squared theta d theta. All right. So we have all the makings of a clean substitution. It just took like, a good half hour to get there. But secant is going to replace the entire radical. dt is equivalent to secant squared. All right, so if we put all that together, and we still have the 1 there with the important variable being theta, what we can do just to keep things a little cleaner and not involve inverse trig just yet, we can leave it boundless, like we were talking about before, and come up with the integral, boundless integral. We'll have to bring back the 0 and 1 later on, but it's going to be secant theta times secant squared theta d theta. All right, secant theta times secant squared theta d theta, which becomes secant cubed d theta, if you want to clean it up. But the thing is, having the benefit of foresight, hindsight, and every kind of sight, / this is my problem, I know that we're going to have to, in the next step, after getting secant squared, secant cubed, go through the process of U substitution. And the first thing we're going to have to do is split it up to secant theta and secant squared theta. So that's kind of cheating on my part, because, if I'm in your position, I wouldn't necessarily know that going in, but just to save time, save energy, we're just going to leave it like this. All right. So then we want to start thinking about, all right, the next step in the process here. So we can make a substitution, and that substitution, so there's a whole lot of substitution going on in this question.
Professor,
What I wanted to do, question?
I'm sorry. And is that the interval from 0 to 1?
We're going to leave it without the bounds for now,
okay.
because that interval only applies to the variable t, and we just converted it over to the variable theta. So rather than converting the 0 and 1 into angular measures, we'll leave it boundless, and then when we convert it back into t form, we'll pop the 0 and 1 back in.
Okay.
So just a quick aside, because we're in straight up review mode here. I'm just going to tuck it in over here. It's never a bad idea. And, in terms of, that jumped. That does that. That's something I got to figure out with this app. I don't know why it does that. Sine squared theta plus cosine squared theta is equal to 1. That's a rule. These are the Pythagorean identities, which doesn't have an R. Other variations of those identities, you could subtract a cosine squared from both sides. You get sine squared is 1 minus cosine squared is 1 minus sine squared, so on. Like, those are possibilities. But we could also divide every term by sine squared. And so we would get 1 plus cotangent squared is equal to cosecant squared. Let me just clean that up a little, make it look a little nicer. So all pre-calc rules, but they come up frequently enough. So it's like, let's just get them down, you know? Going back to the sine squared plus cosine squared is equal to 1, we can divide each term by cosine squared and get tangent squared theta plus 1 is equal to secant squared theta. All right. So when you're thinking about a substitution involving squared values, you might end up looking at your Pythagorean identities. You also might end up working with double angle rules and stuff like that. But again, work from the beginning of the course to the end rather than the other way around, and things start kind of working in the right direction, right? So when you're taking the antiderivative of this, you know, in its current form, even if it's secant cubed, you're not going to be at a point where you can simply just do the reverse power rule or convert it into cosines and be all right with it. I mean, you probably could convert it over the cosine form and maybe do something with that, but it's kind of the long way around. All right. What instead you could do is replace the secant squared with a tangent squared plus 1 and see where that takes you, bearing in mind that it's an avenue. You know, it might not take you where you think you want to go, or it might not take you where you want to go. Ideally, you know where you want to go, but getting there is a different story. Oh, sorry, tangent squared. It doesn't really matter, but I just wanted to keep it consistent with the formula I just wrote. So, d theta. All right, so we can make that substitution and then go from there. All right, so in that part of the process, we now have the product of two expressions. One expression, the secant squared, can be distributed giving us secant theta tangent squared theta plus secant theta, d theta. All right, we can split up our integral. All right, it's a sum, so we can split it by the sum. All right, so splitting it by the sum, we get the integral of secant theta tangent squared theta plus the integral of secant theta d theta. Now that second piece is actually a rule. Well, it wasn't always a rule in Calc 2. I'm sure at some point you had to figure it out. But eventually it became, I mean, if your teacher taught the class anywhere near along the lines of the way I taught it, it was like, all right, you're on the hook for the knowledge at one point, but now it is a trig function. So now you can just rely on it as a fact, right? So secant theta tangent squared theta plus, now this is the rule part of it, the natural log of secant, oh, I forgot the d theta, sorry. I forgot it in the previous step too. I'm not going to throw the plus c in yet. Oh, well, there wouldn't even be a plus c because it's definite. I lost sight of that because of the lack of bounds. But even if it did have a plus c, I wouldn't throw it in at the just yet because it's still have another integral to take, and we can consolidate all that. So making some headway. Now we just got to get that other part taken care of. All right. So now the one thing to keep in mind is if you were to kind of cycle back and say, all right, well, let me replace the tangent squared now, you could run into a problem. But something, or maybe it'll work out, but something to keep in mind, and let me just move some things, just kind of give myself a little bit more space here. Something to always keep in mind is what it is you're looking to find, especially in long problems like this, where things start getting a little crazy and out of hand, and your teacher starts resizing and moving things around, and then you wish that you had the ability to do that. You can tell that this has been a thing in the past. It's very easy to lose sight of what it is you're in fact looking for. So we're looking for secant cubed theta d theta. Right? That's what this whole thing should be equal to. So we can start maybe brainstorming or thinking about different ways you can handle it, but sometimes the approach that you take ends up taking you back sort of seemingly to where you started, and then you say, well, what do they do all this for, right? So one thing that we could do at this point is, because we're at sort of an impasse. So there's two possible ways. If you remember your trig identity integrals, whenever you had secants and tangents together, it was that weird case where it was like, all right, so I know secant tangent is the derivative of secant, and I know that secant squared is the derivative of tangent, so which way do I go, you know? So do I want to convert over and make this secant squared, or minus 1, or do I want to make this a secant tangent separate from the tangent, right? So you kind of, most of the time you just want to play it out in your mind, but sometimes you have to do it on paper to see where you're going to end up, right? So if you play it out by saying, all right, I'm going to save a secant tangent, right? Secant tangent times tangent, right? What would be the benefit of that? Well, I wouldn't want to designate u as secant tangent, because that's just going to make a monster and it's not going to cancel anything out. If I designate the u as tangent, that's not going to cancel out the secant squared. So that's probably not the way to go. All right. Another thing to consider is maybe this is the time to kick it over into sines and cosines and see where that gets you. All right. So that's another avenue that you can take. But another thing that you can do is just kind of go back to where we all started and say, all right, well, we know based off of our identity relationships, right, we have tangent squared plus 1 is equal to secant squared. That means that tangent squared is equal to secant squared minus 1. So see what that does for us, all right? So and, you know, just play this part of it out. All right. Hang on one sec. I'm sorry, folks. You know, something I gotta fix real quick. I'm gonna pause this video. All right, so resume recording. So yeah, so we got, like I said, we got part of it done. We didn't want to lose sight of where we are, where we're going, and all that good stuff. But then eventually you get to either the finish line or a brick wall, and hopefully it's not the latter, but that could be the case. So you might end up kicking over to a different technique, because when you look at this, and, you know, I'll just kind of play it out logically. If I were to distribute the secant to each term on the inside, what I would end up with is something that it's fact-based, but it's not going to be overly helpful. So if I distribute it, I'm going to get secant cubed minus secant. But then I have a secant cubed on the other side, so those will cancel out. So the one thing I was looking for is what's going to cancel out, so that'd be a problem. And then on the other hand, I'll have a negative secant, which I could bring to the other side. So I guess, you know, in a manner of speaking, by using the antiderivative of secant, we've discovered the antiderivative of secant. So this next step, no matter how we slice it, isn't gonna play out the way we want. So in the theme of building from the beginning of the course to the end of the course, we need, or specifically Calc 2, we need a different technique. So we tried use substitution. We started this journey off with trig substitution. It's already in trig form, so we're good there. We're not going to trig it up again. The trig substitution within a trig substitution, that would be insane / fun. Another possibility, since again we only have part of it that we need to worry about, could be integration by parts. All right. So what I would want to do there is find a u and a dv. The u should be something that's differentiable. And most functions, I mean, we can find the derivative of. And the dv should be something that's anti-differentiable. Right? So u, dv, and I'm loosely using the term anti-differentiable here because there are many ways a function could be anti-differentiable. It's anti-differentiable, but in such a way that we could actually carry it out analytically. You know, if it's something like the natural log of 1 over the natural log of x squared plus 72, it's like I don't have faith that, well, it might be something that is differentiable or anti-differentiable. I can't do it. So what I want is something that is anti-differentiable, like on my end, I can handle it, right? So from the secant tangent, I know that a secant tangent squared, I know that secant tangent is the derivative of something. So secant theta, tangent theta, d theta. And the tangent theta would go here. And so we can go through the process of integrating. And so the derivative of my u equation would be du. Right? We really want the du. So I could say du d theta and then move it over, but we're better off just saying du equals secant squared theta d theta. And v would be equal to just secant of theta. All right. uv minus the integral of v du. That's what this result is going to be, right? Secant theta tangent squared theta is somehow going to anti-differentiate using this model, right? So u times, question?
Sorry. Did this happen before the break when you highlighted in yellow secant theta d theta and secant theta tan squared theta d theta?
No, it happened after.
Okay.
I had highlighted something, but then I expanded the highlight to include the whole thing.
Why are they related?
Though they're not related, it's that we're using the integration by parts technique to anti-differentiate this entire expression.
Okay.
The other stuff is already accounted for. I'm not worried about, we got to figure out what secant cube theta is equal to. And we already know that the natural log part is already an antiderivative, so we're good there. This is the only part we're concerned with. Right? So secant theta tan theta minus the integral of v, so secant theta du, so secant cube theta, d theta. All right. Now, believe it or not, this is like the best thing that could have happened. It just doesn't seem like it. All right. So I'm gonna move some things. I'm actually gonna shrink up some of the stuff above it and then move this up. All right, so I have all the other trimmings that come along for the ride. So I got the left-hand side, that's still there. All the stuff on the right is still there. But now I can add the negative secant, that negative secant cube theta d theta. I can add a secant cube theta d theta integral to both sides and consolidate them so that on the left-hand side, I have 2 secant cubed theta d theta. And on the right, I have secant theta tangent theta plus natural log of secant theta plus tangent theta. Still got a fair amount more to do because I need to get this back in terms of t. And yeah, kind of, I wouldn't say I'm regretting not finding the theta values for t. The t equals 0 and 1, but it would have been nice because I would have had that step taken care of, but I would have had to do the work too. So it all comes out in the wash, right? So secant cubed theta d theta would be equal to 1/2 secant theta tangent theta plus 1/2 ln of secant theta plus tangent theta. Close them up. All right, it's kind of like consolidated there a little bit, but you know, it's still a god-awful mess, and there's really no way around it.
Professor,
Hmm.
where did you get the secant cube theta d theta? Why would you put it there? I didn't
On
get
the
that
left-hand
part.
side?
Yes.
Oh, because that's what we're looking for.
Okay.
Yeah, so just kind of, like I said, it's very easy to lose track of this, but on the left side of the page where we have s equals on the integral of 0 to 1, that radical 1 plus t squared dt, when we substituted that all out, that became secant theta times secant squared theta d theta, which is secant cubed theta. All right, so definitely a ride here. I'm gonna clean it up a little bit more so that it's not sticking around at the bottom of the screen, because I know the visuals are a little hard to see when that happens. So I'm gonna move this up a little bit. Well, let me resize, move it up, and then I'll zoom in so we can all enjoy the beauty of this. All right, so now we gotta go back. We gotta convert back. We're still working with a boundless expression, all right? So we're not putting in the 0 and 1 because we're still in terms of theta, right? So I need one of two things. I either need the bounds to be in terms of theta so I can evaluate this, or I need to replace all those thetas with t's, not just replacing them with t's, but a relation that'll replace all the thetas with t's so that I can actually get an answer, right? So that's where, you know, the motivational component comes into play, because in the previous example, it was, hey, you can do it one way or the other. Which way do you prefer? Now it's like, well, you really better think about this, right? So I have a relation between theta and t, a fairly simple relation or relationship if you want. And that is just going back to some of the earlier calculations. I'm gonna go with an orange highlighter. Doesn't really look very orange though. It's like a salmon kind of. I had this relation here, and that is that t is equal to tangent of theta. I had already written it, but I want some room so I can kind of accentuate the thought, right? So a couple of things that I can do. One would be to find the theta equivalent of 0 and 1, so I can do a direct substitution. The other would be to solve this expression for theta and then replace all the thetas with whatever I get as a result, right? So either way, we need to know what theta is equivalent to. And so if I find the inverse tangent of both sides, I get theta is equal to inverse tangent of t. So the question that I would ask myself if I were you is, am I going to swap out this guy, this guy, this guy, and this guy with inverse tangent of t, and then replace all of that stuff with zeros and ones for the simpler boundaries of integration? Or do I want to figure out what theta of 0 is and theta of 1 is, and then just do a direct numerical substitution? All right, I'm going to answer the question for you with what your answer really should be, and that is figure out what theta of 0 is and theta of 1 is, because that's going to make your life a whole lot easier. All right. Now we don't always care about making life easier. Sometimes math is, math. We just want to do it for the sake of doing it. But look at all this work that we've already had to do. Why add more to the pile, right? So inverse tangent of 0, inverse tangent of 1, right? So if you know your unit circle, man, it's like that's going to be a recurring theme in this course. Inverse tangent of 0 is 0. Inverse tangent of 1, you just want to be thinking about on the unit circle, where is the, we're talking about a triangle. Never lose sight of the fact that this triangle is a right triangle in the first quadrant. So, I'm not looking for the 225-degree angle. I'm looking for the 45-degree angle, right? But that 45-degree angle needs to be in radian form, right? So it's going to be pi over 4. All right. So those are the two values that would replace the original bounds of integration. Now, pi over 4 is not too neighborly looking, but really, if you think about it, it's like, okay, it's not the best looking number in the world, but it's a good looking trig number. We'll settle for that. Good looking trig numbers. Those are what we look for. We want like pi over 4, pi over 6, the 2 pi over 3, and stuff like that. All right. We don't want to be dealing with the, like 10. If I told you you had a radian, if I tell you in a whole number system that you're working with the number 10, you're like, oh, that's great. That's a nice convenient number to work with. But if I tell you you're working with 10 radians, you're like, oh, crap. This is going to suck, So that's hopefully where you'll end up being in your own minds before too long, right? So 0 to pi over 4. And so now I can tack that on at the end. I'll use my line draw tool, kind of. And the beauty of this is I don't have to go through the journey of reversing the substitution process. All right. So that's a really, really important piece to keep in mind, because we had already done, we started off with something that was in trig form. We used trig substitution to clean it up, but it was still in terms of t. So we were kind of like excited about that. But then we involved all this trig here. The last thing we want to do is have to reverse course, like all those mountain climbing movies where they show the whole movies I'm showing them getting up the mountain. They never show them getting back down, because that's like a whole nother movie. That's the same idea here. All right. So 1/2 secant pi over 4 tangent pi over 4. If you know these facts, that's great because then you could just cancel stuff out on the fly. Plus 1/2 natural log secant pi over 4 plus tangent of pi over 4. And then minus, yeah, again, streamline if you know it, 1/2 secant of 0 tangent of 0 plus 1/2 natural log secant of 0 plus tangent of 0. All right, so tangent of pi over 4 is equal to 1, so we can get rid of that. Now, we can get rid of it here because it's part of a product. It's a factor of a product. But here, it's going to cancel to a 1, and because there's a sum that's got to stay, it's got to stay there. All right. Tangent of 0 is equal to 0. So it doesn't matter what the rest of this expression is. Here, this is gone. All right. The other part, same idea as before. Tangent of 0 is equal to 0, but it's part of a sum. So we got to hang on to it because the secant of 0 is equal to 1. Now, as it turns out, the natural log of 1 is equal to 0. So the whole thing's going to wipe out anyway, but not because of the trig, but because of the natural log relationship. All right. So at long last, I'm going to finally be able to clean this up somewhat. So 1/2, now secant pi over 4 is the reciprocal of cosine pi over 4, which is cosine pi over 4 is radical 2 over 2, so 2 over radical 2. Right? You could write it in the rationalized form, but then you'll just have to change it anyway in order to cancel some things out. Plus 1/2 ln radical 2 over radical 2 plus 1. So the best I can do at this point is cancel the 2's and leave this as a final answer of 1 over radical 2 plus 1/2 ln 2 over radical 2 plus 1. All right. You could get common denominators and all that good stuff, but once you go down too far in terms of simplifying this, you find that you're just better off putting it in a calculator and going that route. And so, so you might as well just leave it like this. Don't worry about the radicals on the bottom of the fraction. Right? Hopefully, before you got to this class, somebody stopped you and said, "Hey, you remember when they said radicals on the bottom of a fraction are bad? Yeah, they're full of crap. There's nothing wrong with them. You have radicals on the bottom of a fraction. There's absolutely nothing wrong with having radicals on the bottom of a fraction. The only reason why you were ever taught to get them out of the bottom of a fraction is so that you can learn the skill of rationalizing fractions, numerators and denominators. Right? So aside from that, you have radicals on the bottom of a fraction all day long. Right? Sometimes you want to rationalize just in the hopes that maybe it'll clean up a little bit better, but you know, in this case, there's no point. Right? So that's a hell of a solution. And you look at it, it's like, oh man, you spent most of a class on just one question. What is this class going to be all about? This lesson or these two problems was a review of Calc 2. That's why they're there. That's why they're in this packet. It's so that, especially this one question, this is my favorite question, at least to get the course started, because, and it's not designed to scare people. It's designed to say, listen, you're on the hook for this information, but I'm not going to just tell you to go study it and know it and hope for the best. I'll walk you through it the one time at least, so that, you know, okay, what did we talk about? Trig substitutions, use substitutions, and integration by parts, 2 or 3 really important parts of Calc 2. And now you're like, okay, a little bit of a refresher, it goes a long way, right? So hopefully that'll help you going forward.
How did you get the natural log of secant of 0 plus tan 0 into the final answer?
So from secant 0 plus tan 0 to radical 2 over radical 2 plus 1.
Yeah.
Oh, okay. Those are just. Oh, I'm sorry. That all canceled out because secant of 0 is equal to 1, but the natural log of 1 is equal to 0.
So.
So that last bit.
Right. So this natural log is actually from the top. Okay, thank you.
Yeah, no problem.
Okay.